Alright class, this is just a short video on the oxyhemoglobin dissociation curve and the differences between oxygen saturation and your arterial PO2, your partial pressures. So the first thing that we need to understand is, what is oxygen saturation? So oxygen saturation is the percentage of hemoglobin binding sites in the blood that are carrying your oxygen. And so hemoglobin is a chemical molecule in the red blood cells that carries oxygen on specific binding sites. And each hemoglobin molecule, if it's fully saturated, remember that it can bind 4 oxygen molecules to it. Depending on the conditions, the hemoglobin releases some percentage of oxygen molecules to the tissues when the red blood cells pass through those capillaries. And so we measure that, measure how many of these binding sites are combined or saturated with oxygen. And so that number that's given to us is a percentage, and we call that oxygen saturation, or O2 sat. Okay. What is the arterial PaO2? So PaO2, just simply put, is a measurement of the actual oxygen content in that arterial blood. And so the partial pressures refers to the pressure that's exerted on the container walls by a specific gas and a mixture of all the other gases that are available. And so when we're dealing with gases that are dissolved in liquids like oxygen and blood, the partial pressure is the pressure that the dissolved gas would have if that blood were allowed to combine with the volume of gas in a container. So what does that mean? That means that if a gas like oxygen is present in an airspace like our lungs, and then it's also dissolved in a liquid like blood, and the airspace and liquid are in contact with each other, then the two partial pressures will equalize, okay? So now that we understand what each one of those is, we now need to understand what is the oxyhemoglobin dissociation curve, okay? And so this curve can show us some differences in the oxygen saturation and the PaO2, okay? So as the partial pressure of oxygen rises, there are more and more oxygen molecules that are available to bind with the hemoglobin. And so if you look at the chart right here, on this side over here, we have the percent of oxygen saturation in the hemoglobin. And so if you think about it, like 100%, 90% like that, okay? And then across the bottom of the chart, we have the partial pressures of the arterial O2, so PaO2, and it's measured in millimeters of mercury, okay? So as each of the 4 binding sites on that hemoglobin molecule bind to an oxygen molecule, its attraction to the next oxygen molecule increases and continues to increase as successive molecules of oxygen bind. So what that means is, the more oxygen is bound, the easier it is for our next oxygen molecules to bind. And so the speed of that binding increases, and the oxygen saturation percentage rises rapidly on that curve, and that's what we're looking at. As all of the binding sites fill up, very little additional binding occurs, and so we start to level out as the hemoglobin becomes saturated with oxygen. And so the tendency makes it easy for hemoglobin to rapidly pick up the oxygen in the lungs and then pass it through the body. And so as you can see up here, that curve just starts to level out around 90, okay? That's what we're talking about. As the PO2 falls, the hemoglobin saturation also falls, as hemoglobin releases oxygen to the tissues in the areas of lower blood or oxygen supply. Notice around the saturation of 90, let's start right here, that the dissociation curve drops off quickly. So you see this big, there we go, see this big drop here, okay? And this is because the hemoglobin binding sites become less attracted to oxygen as it's bound to fewer oxygen molecules. And so that's what's happening. And so then your deoxygenated blood returns to the heart to be pumped to the lungs, and the cycle just continues to repeat itself. But a normal PaO2, so we got to know what normal PaO2 is. First, let's decide, what is the normal O2 saturation? Anybody? Okay, so 94 to 100 is going to be normal. But for PaO2, our normal is going to be between 90 and 100 millimeters of mercury. So some people may think an O2 saturation of 90 is normal as well, but we know that's not true. So here's how we kind of interpret that. An O2 saturation of 90%, that's right here, 90%, okay? If we go over our line here, and where does it meet this curve? That's going to be roughly 60 millimeters of mercury on our PaO2, okay? So that's the minimum oxygen concentration that's providing enough oxygen to prevent ischemia in our tissues, okay? So once your O2 sat falls below 90%, then your PaO2 is going to quickly drop into dangerously hypoxic range, and as fewer and fewer oxygen molecules are able to be bound to the hemoglobin. So we want to try to keep our O2 saturation above 90%. And when we do that, that keeps our PaO2 up as well. We want it above 60 as well. And so, again, looking at our curve, so if we look here, if our O2 sat is at 75%, holy moly, our PaO2 is at 40. I mean, that's terrible, okay? So you can kind of see that with the oxygen hemoglobin dissociation curve, it shows that percentage of the oxygen binding to the hemoglobin per millimeters of mercury. And as the O2 sat of 90% corresponds to a PaO2 of 60, and if you look at our chart, we can see how quickly it drops off after once it's below 90. It just sharp curve, everything falls off. You kind of think of it as a roller coaster, okay? At the top of the curve, oh, it's really fun, and then, oh my gosh, it's so scary as we go down that hill of the roller coaster. So we want to keep, so when our O2 sat drops below 90, note that our PaO2 is significantly dropping, and now our cells are going to become, cells and tissues will become hypoxic and ischemic, and they're not going to be able to work like they should. So that was kind of the oxyhemoglobin dissociation curve in a nutshell. Something else to think about. So, you know, you're sitting there thinking, well, if PaO2 is more accurate, then why aren't we using that in the field? Why are we using O2 saturation? Well, okay. Oxygen saturation, getting that, it's simple. It's non-invasive. We use our little pulse oximetry readings. They're lightweight, they're easy to carry, they're easy to use. And we know if we keep everything above 90, preferably above 94, we're doing well. But when it comes to measuring the PaO2, we've got to do a blood draw. And then we've got to send it to a lab for it to be tested. Is that feasible in the field? Not really, and it takes time. So we've got to know how PaO2 correlates with O2 so we can get a better idea of what's actually going on with our patients. So if you have any questions on this, feel free to email me, call me, and I'll get back with you and we can talk about it. But until then, you all have a great evening.